Welcome to all of you. In this session, we will go through the design and implementation of digital IIR Butterworth low-pass filter to meet the given specifications and its simulation using the Scilab. First, let us go through a simple problem of designing a digital IIR low-pass filter, that's the Butterworth filter. The question: design a low-pass digital Butterworth filter for the given specification. Passband edge 1500 Hz, stop band edge 2000 Hz, then passband attenuation is 1 dB, then stop band attenuation 3 dB, then sampling frequency is 8000 Hz. Now let us go through the solution procedure. So F1 is the passband edge 1500 Hz, F2 is the stop band edge, that is 2000 Hz, K1 is the passband attenuation, that is given here, and K2 is the stop band attenuation, that is 3 dB, and Fs is the sampling frequency 8000 Hz, which is related with the time as 1 by Ts. Now convert these specifications into the radians. It is given in Hertz, the frequency. We are going to convert that into the radians. So that is passband in radians is given by 2 pi f1 into ts. By resolving this, we are going to get 1.1781 radians. Then stop band in radians is 2 pi f2 into ts, that is 1.5708 radians. Now performing the pre-warping of the signal given by, for passband it is P is equal to 2 divided by Ts tan of PBR divided by 2. We know Ts, we have calculated PBR, substitute it for the passband, we are going to get it as 10690.85. Similarly for the stop band, it is 16000 we are going to get. Then calculate the order of the filter. So this is the formula for calculating the order of the filter. By resolving this, we are going to get 1.667. So as per the Butterworth filter procedure, any fractional value we are going to get must be rounded off to its next integer value. Therefore, order n we are going to consider it as 2. Now let us find the cutoff frequency omega c, or somewhere it is also referred to as omega n. So we are going to consider the stop band specification in order to calculate the cutoff frequency. Therefore, S is going to represent the stop band specification, and this is the formula to calculate the cutoff frequency. By substituting and solving, we are going to get the cutoff frequency as 16019. Now we are going to have the normalized Butterworth filter representation. For order 2, it is given by h of s is equal to 1 divided by a square plus root 2s plus 1. Now apply low pass to low pass conversion by substituting s is equal to s divided by omega n. Now after that, we are going to get h of s as this expression. Now we need to apply the bilinear transformation in order to convert the analog filter into the digital filter. Now substitute s is equal to 2 by ts into 1 minus z inverse divided by 1 plus z inverse in the analog filter, that is h of s what we have obtained. By substituting and resolving, we are going to get h of z as this value. So this was the final digital IIR filter we are going to have. Now let us go through the Scilab simulation for the same. So in the Scilab code, we are going to make a follow-up of the theoretical solution procedure. So this is the passband frequency, this is the stop band frequency, then passband attenuation, then stop band attenuation, and then the sampling frequency. So for whatever the problem that has been solved in the theory, the same has been taken over here. So in the first step, so digital filter specification, we need to convert this frequency in hertz to the radians. So the same formula is being implemented, and then performing the pre-warping part, and then we are calculating the order of the filter as well as the cutoff frequency omega n. So for the order of the filter, whatever the formula that has been discussed, same is being done over here. If we get the fraction, then we are going to round it off to the next value. So that's why CL function is being used. Then the cutoff frequency is calculated with respect to the stop band specification. Then after, we are going to make use of the function IIR in order to identify the digital frequency response, where n is the order of the filter and LP is going to indicate the low pass filter, and this is going to indicate we are performing the Butterworth filter. HZ holds the numerator and the denominator part of the IIR filter output. Then we are going to calculate the frequency response of it, and we are going to plot that response over here. Now let us run this program. So this is what the graph we are going to get. Within this graph, since we are going to make a consideration with respect to the stop band specification, we have to verify the same over here also. So with respect to the stop band specification, if we consider, then 3 dB is the attenuation and 2000 Hz is what we have taken. That 2000 Hz, if we take that in the normalized digital frequency, that is in the range of 0 to 0.5, then we are going to get that as 0.25. Now at 0.25, what is the value we are going to get? So that we need to verify. So exactly at 0.25, if we verify, then we are going to get 0.25. So as you can observe, we are going to get the attenuation value as 3 dB. So it is 2.98, and exactly if we make it equal to, okay, so x-axis is the frequency 0.25 and y-axis is the attenuation in dB, that is 3.01 we are going to get. So what it indicates is whatever the specification we are considered in the given problem, with respect to that we are able to make a cross validation of the same in this low pass filter design. Thanks for joining.